Hello everyone. In the last video, we have seen the Laplace transform, the use of Laplace transform in evaluation of integrals. Okay. In this video, we will find the Laplace transform of periodic function. But before, let us see what periodic functions are. You have already come across the periodic functions. Even then, I am writing that periodic functions. Periodic functions. What are periodic functions? The functions which repeats their values after a particular stage. Okay, like sine function is there, cosine function is there, tan function. All the trigonometric functions are periodic functions. Okay, uh, sine function and cosine function repeats their values after 2 pi of angle. Okay, so let us write the definition first. Periodic function. A function f of t is said to be periodic if periodic with period t if f of t plus t is equals to f of t. Function gives the same value after adding t into its input. Okay, this is what periodic function is. Then f of t plus 2t will be, this can be written as f of t plus t which equals to f of t plus t. Since f of t plus t is equals to f of t, we are considering this as same, this as 1. F of t plus t is equals to f of t plus t. Again f of t plus t will be f of t, since f is periodic with period t. So in this way we can generalize this. Therefore f of t is same as f of t plus t, f of t plus 2t, f of t plus 3t, and so on. Okay, and examples I have already told you. Examples of periodic functions: the sine function, sin x is periodic function with period 2 pi, that is sin x plus 2 pi, you already know this, is equals to sin x. Similarly, cosine function is also periodic with period 2 pi, that is cos x plus 2 pi is equals to cos x. Okay, let us write one more also. Tan x is periodic function with period pi. Okay, that is tan x plus pi is equals to tan x. Okay, so these are the few examples of periodic functions. So now we'll move to the theorem which will give us the Laplace transform of periodic functions. Theorem: let f of t be a periodic function of period t greater than 0, then its Laplace transform is equals to 1 upon 1 minus e to the power minus s t integration 0 to t e to the power minus s t f of t dt. Okay, so let us see the proof. We start from given. Let f of t be periodic function with period t greater than 0. Okay, now by definition of Laplace transform, or we can write that is f of t plus t is equals to f of t. Okay, now we use the definition of Laplace transform. Now by definition of Laplace transform of f of t, we have Laplace transform of f of t is equals to integration from 0 to infinity e to the power minus st f of t dt. Okay, since t is greater than 0, as t lies between 0 and infinity, we can divide this integration into two integration, as 0 to t and then t to infinity. Okay, so Laplace transform of f of t equals to integration from 0 to t e to the power minus st f of t dt, plus the second path is from t to infinity e to the power minus st f of t dt. Okay, we denote this part as I, and we will solve I separately and give this whole equation as number 1. Okay, now I is equals to t to infinity e to the power minus st f of t dt. Here we put t is equals to x plus t, which implies dt is equals to dx as t is constant. And what about limits? When t is equals to t, x is equals to 0, and when t is equals to infinity, x is equals to infinity. We cannot write infinite equals to infinity when t is equals to uh, when t tends to infinity, uh, x tends to infinity. Okay, this is much better than rather writing equals to sign. Okay, so what this integration becomes? I integration from 0 to infinity e to the power minus s t is your x plus t into f of x plus t dt is now dx. Since t is the period of the function f of x plus t will be f of x, and you separate the power of e, this will be e to the power minus sx into e to the power minus s t, and this will be f of x dx. Since f of x plus t is equals to f of x, t is the period of function f, or I is equals to e to the power minus st integration 0 to infinity e to the power minus s x f of x dx. And as x is dummy here, we can replace that x by t, st f of t dt. X is dummy symbol. Okay, uh, which implies, by definition of Laplace transform, this is a definition of Laplace transformation of f of t. So this is e to the power minus st Laplace transform of f of t. Okay, put this value of I in equation 1. What was your equation number 1? It was Laplace transform of f of t is equals to integration from 0 to t e to the power minus t f of t dt, and this was your I whose value we just evaluated. Okay, so let us write that down. So this is Laplace transform of f of t. The second integral we have integration from 0 to t e to the power minus st f of t dt plus, what was the value of I? E to the power minus st Laplace transform of ft. Okay, so you now shift this second term on right hand side onto the left hand side and take Laplace transform of f of t common. You will get 1 minus e to the power minus st into Laplace transform of f of t, which equals to integration from 0 to t e to the power minus st f of t dt, or Laplace transform of f of t equals to 1 upon 1 minus e to the power minus st integration 0 to t e to the power minus st f of t dt, which is what required. Okay, so whenever ft is a periodic function with period t, its Laplace transform is this 1 upon 1 minus e to the power minus st into integration 0 to infinity, 0 to t e to the power minus st f of t dt. So let us have one example. Find the Laplace transform of the function f of t defined by t when t lies between 0 and a, and 2a minus t when t lies between a and 2a, where f of t plus 2a equals to f of t. So whenever you see this, it should be clear to you that 2a is the period of the function f. Okay, so f of t is a periodic function, so you have to use this equation. Okay, solution. Let f of t be a periodic function with period 2a, that is f of t plus 2a is equals to f of t. Now we use the definition of Laplace transform of f of t. Now by using definition of Laplace transform of periodic function f of t, we get definition means what result we have proved in the last theorem, this. Okay, so we get here Laplace transform of f of t equals to 1 upon 1 minus e to the power minus s t. T means period, and here period is 2a, so here it will be minus 2as, okay, into integration from 0 to t, that is 2a e to the power minus st f of t dt. So now what will be the next step? It is 1 upon 1 minus e to the power minus 2as. You now divide this path into two. One path is 0 to a e to the power minus st f of t dt, and other path as a to 2a. This is the property of definite integrals, e to the power minus st f of t dt. Okay, next 1 upon 1 upon 1 minus e to the power minus 2as. So here in the first integral range is 0 to a, and in the definition when t lies between 0 to a, ft equals to t, and when it lies between a to 2a, it equals to 2a minus t. We use this definition of f of t in this bracket. So integration from 0 to a e to the power minus st f of t will be t here, and when t lies between a to 2a, f of t is 2a minus t. Okay, so you have to solve these two integrations, as there is a product of two functions. Here also same, the product of two functions, you have to use integration by parts. So let us do that. Laplace transform of f of t, 1 upon 1 minus e to the power minus 2as. Applying the integration by parts here. First into integration of second, which will be e to the power minus st upon minus s with the limits 0 to a, minus integration of derivative of first function, that is t, which will be 1, into integration of second function, which will be e to the power minus t upon minus s. Okay, next integration, first into integration of second function, which is e to the power minus st upon minus s a to a. Okay, minus integration of derivative of first function, that is 2a minus t, that will be minus 1, into integration of e to the power minus st, which will be e to the power minus st upon minus s dt. Okay, so the next step, Laplace transform of f of t equals to 1 upon 1 minus e to the power minus 2as. See, at upper limit this will be e to the power minus as upon minus s, okay, and at lower limit, because of this t, the term will be 0, so we are not going to write that. So this is minus integration of e to the power minus st will be e to the power minus st upon minus s. That minus s and this minus s will be plus s square 1 upon s square, okay, and integration is e to the power minus st with limit 0 to a, plus at upper limit, that is at t is equals to 2a, this 2a minus 2a will be 0, so first term will be 0, minus at the lower limit, that is at t is equals to a, this will be 2a minus a, which will be a, okay, into e to the power as, sorry, minus as upon minus s, or we can write this plus 1 upon s, okay. Next term, this minus 1 and this minus is plus, and integration of e to the power minus st is e to the power minus st upon minus s, that minus s, this minus s will be 1 upon s square e to the power minus st with the limits a to 2a, okay. So this is Laplace transform of f of t equals to 1 upon 1 minus e to the power minus 2as. See, this term and this term are same with opposite sign, so these two will get cancelled. So we write this term at upper limit, this will be minus 1 upon s square e to the power minus as, and at lower limit this will be plus 1 upon s square e to the power 0, that is 1, okay. This is cancelled. What about this? This is 1 upon s square e to the power 2a s, okay, minus at the lower limit 1 upon s square e to the power minus as, okay. So we can take 1 upon s square common, we get Laplace transform of f of t equals to 1 upon 1 minus e to the power minus 2as, okay. We are taking 1 upon s square common, so what remains inside this e to the power minus as and this e to the power minus as, which is 2 times e to the power minus as, okay, minus 2 times, this is taken common, and what about this? This will be plus e to the power minus 2 as. So rearranging the terms, Laplace transform of f of t is equals to 1 upon 1 minus e to the power minus 2 as. This can be written as, or this can be given as e to the power uh, minus 2 as plus minus 2 e to the power as plus 1. This is uh, nothing but 1 minus e to the power minus as whole square, okay, into 1 upon s square. One more thing we can do here, in the denominator of this fraction, as this is 1 minus e to the power minus 2 as, this can be written as 1 plus e to the power minus as, 1 minus e to the power minus as, like a square minus b square. This can be viewed as 1 square minus e to the power minus as square, and so the formula. This is 1 minus e to the power minus as whole square 1 by s square. So one bracket from denominator will get cancelled with one bracket in the numerator. So we have Laplace transform of f of t equals to 1 minus e to the power minus as upon 1 plus e to the power minus as into 1 upon s square. So this is the required Laplace transform of periodic function f of t. This was the last example of this unit. Okay. So let me give you one example to try out. You take this example as your assignment. This is very similar to the example we just did. Find Laplace transform of f of t equals to a sin pt when t lies between 0 and pi by p, and ft0 when t lies between pi by p to 2 pi by p, where f of t equals to f of t plus 2 pi by p. That means 2 pi by p is the period of f of t. You try this example as your assignment. So hope you did understand this whole unit. In the next video we will start our next unit, that is inverse Laplace transform. Okay, but before moving into that unit you must go through all the topics in this unit. Okay, so till then, goodbye.